Hello, my name is Keir Groves and this is my video presentation for IROS 2020. The title of the paper is Model Identification of a Small Omnidirectional Aquatic Surface Vehicle. I'm a research fellow in the Robotics for Extreme Environments group at the University of Manchester in the UK, and my research focus is mainly on aquatic vehicles that operate in confined spaces. A lot of our work at Manchester is with the nuclear industry, so fuel storage pools is a primary application area for our aquatic robots. The present work concerns an aquatic surface vehicle named Mallard that you can see here, and it was designed especially for inspection and monitoring of nuclear fuel storage pools. So in this video you can see an early version of Mallard operating in a mock-up of a fuel storage pool. And here Mallard drives autonomously around the pool and inspects the stored fuel below, and the fuel here is represented by the shapes on the floor of the pool. And the present work is about building a dynamic system model of Mallard. So the question to answer is, why do we need a dynamic model? And here's three reasons. First, to facilitate development in simulation. With an accurate dynamic model, our simulations will match the real world much better, and it will allow us to do testing and development in simulation. Second, to improve the trajectory tracking control system. Now this can be done in two ways. We can either use the model to implement a model-based tuning procedure, such as IMC tuning, for our current PD controller, or we can facilitate the development of a more advanced model-based controller. And finally, we can improve the robustness and precision of the location estimate by providing odometry information from the system model that's generally not available on this type of robot. This paper has three key contributions. First, the development of a dynamic model structure that's suited to small omnidirectional surface vehicles such as the Mallard platform. Second, a methodology for identifying model parameters that can be rapidly implemented without specialist equipment or facilities. And finally, an alternate thrust allocation scheme that improves the accuracy of the dynamic model by avoiding deadbands. Now I'm going to move on to talk about the dynamic model. The job of the dynamic model is to relate the joypad inputs FU, FV, FR to the velocity of our system, seen here as capital Nu, and we do this by solving this equation of motion. The first term on the left is the inertia vector. The second term is the vector of centripetal forces. The third term is the vector of drag forces, and finally on the right we have the vector of propulsion forces and moments. The choice of terms used in this dynamic model was based on observing motion of Mallard in response to different thrust inputs, and also on the significance of certain parameters. Extra parameters were trialled and then removed again if no significant impact was made on the model accuracy. So in the mass matrix we can see we have both mass and inertia terms. In the drag matrix we have linear drag terms and we have non-linear drag terms, and we also have cross-coupled, we have a single cross-coupled non-linear drag terms, and we have linear force terms. In the present work we use two thrust allocation schemes. The first one we use is a standard scheme called the Moore-Penrose allocation. We call it the MP allocation. In this case, this is a standard method whereby you relate the impact of each thruster to each degree of freedom and build a matrix and then invert it so that we then have the joypad inputs FU, FV, FR, those as inputs, and then the resultant is each of the individual thruster outputs. The second thrust allocation scheme is one that was devised by the authors to avoid deadbands in the thruster response. Instead of using the complete thruster response in forwards and backwards, we avoid the deadband and only use this area of the thruster, so the thrusters are always turning forwards. To implement this, we set all the thrusters at a base level of motion, so we turn all these thrusters on to the same amount, and because of the configuration of the thrusters, that will cause a net zero force in FU, FV, FR. Then if we want to move the robot in a particular direction, we turn on two thrusters. So if we want to move forwards in FU, we turn up the inputs to F1 and F2. If we'd like to move backwards, we turn up the inputs to F3, F4. If we'd like to move in Y, in positive Y, then we turn up F2 and F4. And if we look to move in negative Y, we turn up F1 and F3. And we do a very similar thing for rotation as well. So this thrust allocation allows us to avoid this dead band here and use this largely linear area of the thruster response. Okay, now on to data collection. So all the data for this experiment was collected at our test tank at the University of Manchester. And for these tests, we drove Mallard around in the pool and we collected Mallard's pose in the Earthix frame and the joypad inputs also. For each of the two thrust allocations, we took a total of 7 sets of data, sets S1 to S7. Sets S1 to S3 we use for model identification, and sets S4 to S6 are a repeat of S1 to S3, and they're used for the initial validation. And then set S7 is combined motion, and that's used for the final validation. So a little more information on what's in these data sets. In set S1, Mallard's motion was dominated by thrust in the x direction, so FU, and as much as possible only thrust in the x direction was exerted during set S1. Thrust in FV and FR were only used to stop Mallard from crashing into the walls. Similarly, in set 2, the thrust was dominated by FV, so we kept the motion as much in the Y degree of freedom as possible. And then finally, in set S3, we excited as much as possible in FR, so in the yaw. So the 3 sets were largely containing only a single motion in a single degree of freedom. The data sets S4 to S6 are repeats of S1 to S3, so again with motion only in a single degree of freedom per data set. And then finally in data set S7 we performed combined motion where we used all 3 inputs, FU, FV, FR, and we drove around in different patterns that would be representative, such as in stripes and in figure of 8s and in circles. To perform model identification, a standard least squares method is used, and to do this we use the equations shown previously and we multiply them out and group constants, and the result is shown here in these equations. Using measurements from the datasets S1 to S3, the model coefficients are determined in 4 steps. First, the uncoupled coefficients are estimated for each degree of freedom. So in the first step, dataset S1 is used to determine the uncoupled X coefficients. In step 2, dataset S2 is used to determine the uncoupled Y coefficients. In step 3, dataset S3 is used to determine the uncoupled psi or yaw coefficients. And then finally, in step 4, we use dataset S1 again to determine the coupled coefficients that relate motion in the X direction to motion in the psi direction. Now we have 2 dynamic models, one derived from the MP thrust allocation and one derived from the AF thrust allocation. And the performance of these different models are compared using datasets S4 to S7. In these results, our models are run at 15 Hz, and all of the results here are based on a 15 step ahead or 1 second velocity prediction. The plot you can see here shows predicted velocity against measured velocity for dataset S5, which was dominantly Y motion, and this is for the Moore-Penrose thrust allocation. To generate a velocity prediction at a given time, we take the measured velocity from a second before, and then we run the system model recursively for 15 steps to achieve a predicted velocity at the current time. As you can see, the dynamic model here performs reasonably well, and the predicted velocity tracks the measured velocity quite well. This was true across all of the data sets and for both of the dynamic models used. This table compares the RMS errors in velocity prediction for the dynamic model based on the MP allocation and the dynamic model based on the AF allocation across the three datasets S4, S5 and S6. As you can see, both models produce reasonably low error, but the AF allocation model consistently outperforms the MP allocation model. Finally, I present the results from dataset S7, where we had combined motion across the degrees of freedom. So we drove the robot in circles and stripe patterns and square patterns and other representative types of motion. The three plots on the left show velocity predictions for the dynamic model based on the MP allocation in all three degrees of freedom, U, V and R. On the right hand side we have a matching three plots only for the AF allocation, showing the measured against predicted velocities. Visually we can see that for the AF allocation, measured velocity matches predicted velocity much better than for the MP allocation. This is also shown in the RMS errors across the three plots. So for X and Y, the AF allocation always beats the MP allocation, but not by a significant amount. However, for R, the AF allocation shows a much higher performance, and we can see that also in the plot. And the R performance is very important for the dead reckoning ability of the model. We can also see the improved performance in the histogram plots. So we can see that for the AF allocation, the histograms show a much more Gaussian shape, meaning the noise has less structure, which typically means the model has been better identified. Some conclusions of our work. We've suggested a dynamic model structure for small omnidirectional vehicles, and we've given a practical method of obtaining the model coefficients for this dynamic model. And a key point to make about this is that all the data used to obtain the coefficients was taken from the sensor packages already on the robot, so no additional equipment was required. We evaluated the performance of two dynamic models, one based on the Moore Penrose inverse thrust allocation and one based on a thrust allocation suggested by the authors. We found that both dynamic models perform well, but the AF thrust allocation model performed consistently better than the MP thrust allocation model. And it's good to note that the dynamic models that we derived are currently being used by the authors to develop our systems offline in simulation, and also for the development of more advanced trajectory tracking controllers. Thank you for listening. This work was presented as part of the EPSRC program grant, Robotics for Nuclear Environments. If you want any more information about our work on this grant, you can go to this website, nuclearrobots.org, or if you'd like more information about the work that we do at the University of Manchester on robotics, you can go to the second website, umrobotics.com.